This is the first in a series of videos about collision theory, which is related to kinetic molecular theory, which we talked about in the gas law chapter. So we're going to talk about the three facets of collision theory. Then later we'll look at reaction diagrams. We'll look at the Arrhenius equation, and we'll talk about how to find the activation energy from data. So I have cheated and written the three facets of collision theory here. So pause the video here and write them down. Okay, hopefully you're back. So now let's talk about these facets. So collision theory is related to kinetic molecular theory. It's used to describe gases and how they move, how they collide, how they create pressure, and what they do and don't do. So kinetic molecular theory was all about what sorts of collisions cause pressure, what sorts of interactions particles had with each other, and how gas particles move. And so this facet, this collision theory, is part of kinetic molecular theory. It's specifically about what happens when there are collisions between molecules. So for a reaction to occur, reactant molecules must collide with each other. Not always. So if you only have one molecule in the reactant and it's a decomposition, then obviously that reactant can decompose whenever it wants to. But if there's at least two atoms in the reactant, then those two reactant molecules need to run into each other for a reaction to occur. So this collision theory that we're going to talk about helps us predict the kinetics of a reaction, because this chapter is about kinetics, about how fast things happen. And how fast a reaction happens is related to how many collisions happen and whether they are useful collisions or not. So let's have a look at the first facet of collision theory. So this is the first facet, and it says the rate of a reaction is proportional to the collision frequency. So the factor we're going to be talking about is collision frequency, and that's related to a rate. So we can write that with our proportional symbol like we're used to seeing. So we can write the rate is proportional to the collision frequency, and a collision frequency is just a number of collisions over some amount of time. It's just a different kind of a rate, except instead of using concentration, we're counting the number of collisions. And if you reach way back to the first video on this chapter and you remember the 5 factors that affect the rate, you'll remember factor number 3 was the concentration. And so concentration affects the number of collisions per unit time. So there's a couple of different ways we can change the concentration. One of the ways we can change the concentration is by actually putting more molecules in the container. So let's draw ourselves some containers of gas here. Okay, and this is going to be a picture of amount. So let's say we had a flask and it had some number of molecules in it. We could increase the concentration and increase the number of collisions by putting more particles into the container. So now there's the same size space with more particles. They're going to be running into each other more often. So we'll call this one fewer, and this one has more. And this one, the one that has more particles in it, is going to be the one with more collisions. Has a higher collision frequency, and so the rate of the reaction is going to be higher in this container. Okay, the other way we can increase the concentration for a gas anyway is by changing the volume, because changing the volume changes the pressure in the container, like we learned in the gas chapter. So if I had a really big container and it had some number of particles in it, let's say it has 5 particles. This is going to be the volume comparison. If we wanted to increase the concentration in this container without adding more particles, we could simply decrease the volume that these were present in. Remember, because concentration is amount over volume. So I could squish those same particles into this very small container, maybe. There we go. So they're very tight. There's going to be a lot more collisions in this container. So this is going to be a large volume. This is going to be a smaller volume. And so this one, we decrease the volume and increase the pressure, is going to have more collisions. There we go. So facet number 1, the rate of the reaction is affected by the collision frequency. We can change the collision frequency by increasing the amount of particles or by changing the volume and therefore the pressure of the container. Okay, now let's move on to the second facet. The second facet of collision theory is going to be about orientation. And it says the reactant molecules must collide in a particular orientation that allows contact between the atoms that will eventually be bonded together in the product. So contact between atoms that will be bonded in the product. That's what we're looking for. We're looking for them to come together at the right angle. So here's an example reaction. This is at the reaction of N2O plus NO, going to make products N2 and NO2. So let's look at what the shape of those molecules look like. I'm going to be using green for nitrogen and red for oxygen in this case. So N2O is a fairly linear molecule. So I'm going to draw circles for each of the atoms. NO is also a linear molecule. N2 is a linear molecule. And NO2 is bent, much like water. So it looks a little bit like this. So this is what we're going to. So if we think about the bonds that are changing, in the N2O, we have nitrogen, nitrogen, oxygen, and it is changing into N2. So that oxygen molecule is coming off and it is being given to the NO. So we're looking to add it right about here onto that NO molecule. That's where we're hoping to put that oxygen. So when we collide these, we need to make sure that the atoms that are eventually going to be connected are going to collide with each other. So let's draw some examples of the angles they could collide at and decide whether or not those would work. So first, let's try colliding them in the way that I've drawn them in the picture. And we'll take some time to color because we've spent a lot of time doing calculations in the last couple weeks and we really need a break. All right, so let's say we collide the molecules at this angle. We are going to be colliding an oxygen with a nitrogen, and that is the new bond that needs to be formed. So that is going to be a good orientation. But the orientation isn't necessarily going to look like that. So what if we collided them and we collided the two oxygen ends together? Like so. So we've got the N2O with the oxygen end and the NO with the oxygen end. running into each other. If we collide the two oxygen ends, we're not looking to form an O2 bond, we're looking to form an NO bond. So we're not colliding the correct molecules together. So that collision is not going to produce this reaction. They're just going to bounce off, or they're going to do a different reaction. All right, and then let's try, we've tried oxygen reacting with nitrogen. We've tried oxygen hitting an oxygen. So let's try a nitrogen hitting a nitrogen. We do a lot of drawing in chemistry, but it doesn't have to be beautiful. It just has to get the point across. Okay, so if we did a collision at this angle, we're contacting two of the nitrogens together, and we are trying to make a nitrogen-nitrogen bond, but we already have one. So we're not trying to form an N2 bond, we're trying to move that oxygen from one thing to another. So if we're not reacting an oxygen, if we're not colliding an oxygen, this is not going to be helpful. So this first drawing, this is the only orientation, something that looks approximately like this is the only orientation that matches the way that the atoms are supposed to be bonded in the product. Okay, so number one, collision frequency affects the rate. Number two, orientation affects the rate. Now we're going to do number three. I'll give you a minute to write this down since I've pre-written it. Okay, so the third facet is going to be about energy, arguably the most important one. So the collision must provide the minimum kinetic energy needed to break the bonds in the reactant molecules. So this is a concept that's often not intuitive. So bonds behave in the same way as magnets. You've probably learned about this before, but we're going to review it again here. So we need to think about what happens when we try and pull magnets apart and what happens when we try and bring magnets together to form a bond. So breaking a bond is like pulling a magnet apart. It requires energy input because it's difficult to do. The two magnets stick together really well and you have to pull really hard to get them apart. Forming bonds, like allowing two magnets to attract each other, releases energy. It's very easy to do. When you hold two magnets close to each other, they jump to bond together. They jump out of your hand almost to be bonded together. You don't have to put in any effort to get them to do that. So this is the one that's related to this process. So we're trying to break bonds in the reactant molecules, and that is going to require energy to do. So let's draw some pictures of what that might look like. So for breaking bonds, let's think about, we have two magnets or two atoms that are bonded together. If we want to break that bond, we might lasso around each of them. And we can draw some little people that are trying to pull those two apart. So they're working hard. It's a difficult job. So we're trying to move the two atoms this way, trying to pull them apart. It's difficult. It's like pulling apart two magnets. We have to put in energy. It's going to be an endothermic step. All right, let's draw the opposite one. Forming bonds. So if we have two atoms and they are close enough together that they could form a bond, they're going to be moving towards each other. That is going to be a super easy step. So we can draw some lines showing this is going super fast towards each other. And if we put our lassos back on, here's some little people. They're just being dragged away by how fast they're running to bond to each other. There we go. Little cartoons never hurt anyone. So when you're breaking a bond, it's like trying to pull apart two magnets. It's really difficult to do. Energy needs to go into the process. And when a bond is forming, they run into each other and they actually release energy because they're moving so quickly. Just like when two magnets jump together. All right, so to summarize those three facets of collision theory, let's draw a little memory device here. There's going to be three facets, and those facets are going to be collision frequency. And for collision frequency, we drew a picture of molecules in a box. We said we could increase the concentration in the box, and that increased the collision frequency. Our second facet of collision theory was we have to have the correct orientation. So it's going to matter which way the particles run into each other, which end is on the left, which end is on the right. And our third facet of collision theory is energy. Energy is about how difficult it is to break the bonds in the reactants, to pull those atoms apart. I hope you have enjoyed these doodles, and I hope hope that they help you remember the three facets of collision theory. And the next video, we'll talk about the third facet, energy, a bit more, and about how we can discuss how large and how much energy we need to do a particular process.